Here we are in Canvas. This week's module is mostly done. I just have to get the discussion board put together for after Friday's class. So today we are starting our next unit. We're going into unit 5, which is exponential functions, and we're going to be looking specifically starting with exponential growth. If you don't know what that is okay. That's what we're going to be learning about. As far as the assignments and such, we will have our live class resources. Those will be populated today after class. There is no discussion board for today. Instead, I have our Unit 3 self-assessment assigned, and then we'll only have one other discussion board. So there'll still just be, there's only going to be 2 assignments this week. Granted, one of them is the self-assessment. The self-assessment here is set to be due November 23rd. All right. That's in just under 2 weeks. The self-assessment is the same as the first one that you guys did. It consists of a problem, and then a reflection, and then you get to choose your grade based on your current level of understanding. All right. In this self-assessment, we have this. This is the problem. This is your demonstration of understanding. There's a few parts to it. I recommend working it out on paper, all right, and then just taking a picture of that and uploading it. You can attach a picture as a file, or you can embed a picture in the text editor. It just depends on which version of the text editor you're using. There are 2 possible versions within Canvas. I prefer this one because it's a little easier to use. If you want to change that, you change that in settings. All right. If you're using the other text editor, you will have to attach the image as a file. And then I'll be able to click the file, look at the image, and look at your work. I just think that is easier to do than trying to type up everything that you've done and show your work with a keyboard. All right. So there's that. There's the reflection. And then you select your current level of understanding based on what you've done. I do need to edit that. Okay. And that's it. That is the self-assessment. All right. Any questions about the self-assessment for Unit 3, our linear functions unit that we just finished? Okay. All right. All right. So then, and there we go. Tomorrow there is no school. It is a day off. Thursday it will be a 1-3-5 block day, and Friday will be a 2-4-6 day, just as it normally would be. And we'll continue with our unit on exponential growth on Friday when we get there. All right. So that is what the week looks like. There are only 2 assignments that will happen this week, that will be assigned this week. There is the self-assessment, and then there will be a discussion board on Friday. And that's it. Those are the only 2 assignments. All right. Any questions at all about this week? About Canvas this week? Okie dokie. So then we're going to get started. If you're taking notes, there will be some things you may want to take notes about. So you might want to get that ready. All right, here we go. So it is Tuesday, November 10th, 2020, and this is our introduction to exponential growth. So first we have a scenario here. And I'd like you just to type your response to this question once you see the scenario and the options here in the chat, please. All right, so our scenario is here. You're starting a new job. Your new company is offering you 2 salary options. Option number 1, you get $10,000 a day for the first 30 days. Right, day 1 is 10,000, day 2 is another 10,000, day 3 is another 10,000, and so on. Each day you get 10 grand. Option 2, you get a penny a day doubled every day. So the first day you get a penny, second day you get 2 pennies, third day you get 4 pennies, 8, 16 cents, and so on. All right. So that's the scenario. Which option would you choose? Please type your responses in the chat. Would you choose option 1 or would you choose option 2? Miguel's going with option 2. Ari says option 2. Ariana's option 2. Isaiah's option 2. Okay. Nicholas says option 1. Savannah said option 2 as well. Judith's option 2. Isabella says option 2. David's on option 2. Okay. All right, someone who chose option 2 or option 1. Give me a reason why. Let's start with option 1. Someone who thinks option 1 is better, tell me why. You can type it in the chat or you can unmute your mic. Okay. So Nicholas, yeah, if you need the money right away, option 2 might take a little longer, right? Carlos saying option 1, okay. So option 1 might be better if you need money now. Okay, that makes sense. Someone who thinks option 2 is better, can you give me a reason why? Okay. Right, so Ari and Miguel are kind of both saying the same thing. It's going to grow more over time. And it's going to get to massive amounts. Right, it goes on every day. The other option is only for 30 days. Yeah. What if both options were only 30 days? I know the second option doesn't say that it's only 30 days, but what if both ended at 30 days? Would you still choose option 2? All right, Savannah says if it's only 30 days, she'd probably go with option 1. Miguel says no. All right. So you guys think that in a 30-day time period, option 1 will most likely make you the most money? Right, that's essentially what we're going after. Which one's going to make you the most money in 30 days? Let's put it at that. Is that kind of what we're feeling? Yeah, so now we're switching to option 1. If we're only doing a 30-day time period, we're looking at option 1. Okay. All right. Well, let's look at the math. Let's see what happens. All right. So, as we assumed, most likely you chose the option that seemed to make the most money in 30 days. So we're going to look at the math here. Option 1 is 10,000 a day for the first 30 days. So we have 10,000 plus 10,000 plus 10,000, 10,000, 10,000, 30 times 10,000. Right, we're doing 10,000 plus 10,000 30 times, so that gives us 30 multiplied by 10,000. Right, that's where the 30 goes. Option 2, we get a penny a day doubled every day. So we started a penny and we multiplied by 2 every day. All right, so we multiply by 2 30 times. That 30 becomes this exponent attached to the 2. All right, so now after 30 days, option 1, we got $300,000. That's a pretty nice chunk of change, right? We're doing all right. Option 2 is a little higher. By a little, I mean a lot. Why? How did that happen? We started at a penny. And we got to 10.7 million. What caused option 2 to increase so much faster? Essentially, yeah, it's doubling every day, right? That multiplication times 2 every day, right? So initially, like that first week, as a couple of guys said, like if you need money right away, that first week's probably not going to be great. That first like 7 days, you're not getting a ton of money, but eventually, right, you're doubling larger sums, right? Once you get up to like full dollar amounts, right, it's going to go quick. So yeah, essentially, yeah, it's that multiplication factor, right? It's being multiplied over and over and over and over again. Does anyone know what this little number is that's above the 2, 2 to the 30th here? What do we call that number? Does anyone remember? Yes, Ari, that is an exponent, which is why this is called exponential growth. We're going to be using lots of exponents in this unit. All right, now, I think we already talked about this part. Yep. So the operation that's occurring in option 2 as opposed to option 1, right? In option 1, we're doing repeated addition, right? With repeated addition, when we do repeated addition, how do we show that mathematically? Right, rather than doing like, 2 plus 2 plus 2 plus 2. How do I show that in like shorthand in math? Rather than writing 2 plus 2 plus 2 plus 2 plus 2 5 times. All right, we're looking at addition though. Sorry, we're reversing a little bit here. When I'm adding the same thing over and over again, how do we show that mathematically if I have 2 plus 2 plus 2 plus 2 plus 2 plus 2? Right, we just say multiply that number by 5, right? Repeated addition, when we're repeatedly adding the same number, we just multiply by the number of times I've added, right? I have 5 2s, right? I have 5 2s here. So then I multiply 2 by 5. So when we have repeated addition, we use multiplication to write that in shorthand. With option 2, we're doing repeated multiplication. Right, so it's like we're going 2 times 2 times 2. Right? And we do this 5 times. In this case, right, as Jocelyn and Nicholas we're jumping ahead to here, we're using the exponent, right? 2 to the 5th power. Right, so this 5 goes into the exponent spot to say, okay, I'm multiplying 2 by itself 5 times. Right? Repeatedly adding the same number, right? This will give me a result of 10. If I'm multiplying 2 times 2 times 2 times 2 times 2, 2 to the 5th power, right? That's going to give me 32. So the rate at which the number grows is faster. It's exponential, as they like to say. Okay. Is there any question about the difference between repeated addition and repeated multiplication? So what this kind of gets to here, repeated addition is what we just did in our previous unit. Right? Linear functions, the rate of change is adding the same number or subtracting the same number every time from a certain start value. That is linear. Repeated multiplication or repeated division, which we'll get to at another in the later part of the unit. That is exponential. Okay. Mess that up. So, okay, we're going to look at another example of exponential growth. The next part here, but I need to make sure I've shared my audio. So I need to do that. All right. That should fix it. All right. So next, come on, please load. Yeah. All right. So I'm fairly certain none of you guys have seen this movie because, or maybe one or two of you might have. The movie is called Pay It Forward. I don't remember when it was released. It was either the very like 99, 2000, or just after 2000. So it's older than you guys, but it's a great example of this little scene here of exponential growth. So we'll watch this and hopefully it cooperates with me. Hopefully it's not too loud.
This is your assignment. Extra credit, it goes on all year long. Now, wait a minute. What's wrong with this? What's the matter? Yes?
It's like so...
So what? There must be a word to finish that sentence. Someone help her?
Weird. Crazy.
Weird. Crazy.
Hard. Bummer.
Bummer. Hard. How about possible? It's possible. The realm of possibility exists where? In each of you. So you can do it.
That's me. And that's 3 people. And I'm going to help them. But it has to be something really big. Something they can't do by themselves. So I do it for them. Then they do it for 3 other people. That's 9. And I do 3 more.
That's 27, so I'm not really good at math, but it gets big really fast, you know?
Yep.
All right. A little articulation, please.
Yes.
I think it's a good idea.
Sean?
It's stupid.
Adam?
It's the honor system. People blow off the honor system. So what? Just because you do.
Well, Trevor, the class seems to think that you've come up with an overly utopian idea. Look that word up in a minute.
Like a perfect world?
Mm-hmm.
So?
Alrighty. So the big idea that we're taking away from this is the idea of exponential growth, right? The picture that essentially the kid drew, right? Showing how this thing expands. It's kind of a visual representation that we're going to look at to help make sense of exponential growth. So in his diagram, it started with 1 person, right? And that 1 person helped 3 people, right? Each of these people helps 3 more. Right? In this diagram, this first person, the one that kicks it all off, the starter here, right? This would be considered level or stage 0. This is the starter. They haven't received a good deed. They're starting it. Right? The next 3 people, that's going to be stage 2 or stage 1. They're the first people to receive a good deed. Right, and then the next level is stage 2. And so on. And we can see at stage 1, right, there's just one person. Then we go to 3. Then we're at 9. As we continue, if we did another stage, which, let's see. Right, we can continue this. After about this stage, it gets really hard to draw. But this also gives us a really nice visual on how quickly this expands. Right? Gets really big really quick, as they said in the video clip. Right? So at stage 3, right, this level, how many people have been helped? Or how many people were helped at that level? Yeah, Jocelyn, that's correct. 27. Right? So we have this picture here. This is our visual representation, which we can do with kind of an exponential growth here to see how it's growing. It's another visual thing besides a graph that we can use. Right. Does anyone have any questions about the tree diagram? Okay. So now let's finish this table. All right, we already filled in the 3rd stage. That was 27. What's the number of good deeds for the 4th stage? Right, how many people are helped in the 4th stage of this? Yes, all right, that's right, 81. All right, what about stage 5? 135. It's not 135. That's a good guess. It's a good attempt. I'm trying to figure out how you got that number. So think about yes, 243, yes. That is correct. And then the sixth stage, 27, 81, 243. What's next? Yep, 729. I think Ariana found the pattern. And the last one on our table here, seventh stage. Yes, 2,187. So, Ariana, because you had the last few answers, it looks like you found the pattern. What were you doing to get from the number we knew to the next number? Yeah, multiplying by 3, right? So Ariana was, took 27, or well, she's 81 times 3. That gave me that number. Then we said, okay, 243 times 3, 729. 729 times 3 equals 2,187. Right, so each step along the way, we're multiplying by 3. Right? So the rate of change, so to say for this function, for this table, for this process, right, is multiplying by 3. Right? In our previous unit, all of our rates of change were a consistent number being added. Right? The rate of change would be 2, and we add 2 each time. In this case, if we're just looking at what's being added, that number changes each time, and we can't use that anymore as a rate of change. So we have to look to multiplication here. All right, so we get a rate of change here of times 3, right, which is what we answered already. All right, so our pattern of change, right, is multiplying by 3, as Ariana stated. Right, so the multiplying by 3, that is essentially our rate of change. So within this part of the unit where we're talking about exponential growth, we're looking for a number that we multiply by each time for our rate of change. Right? This is what the graph of that would look like. Right? Notice that it starts really kind of like level, and then all of a sudden it just fires up. Right? It just goes boom, like straight up. Right? If you've seen any of the graphs for like when COVID-19 first started back in March and April, and they were saying it modeled an exponential growth, it's because this is what happened. This is how it spreads. Right? Just like the little diagram that we showed with the one person, and they come in contact with all these people and they come in contact with more people, it exponentially grows, right? Starting with a single person, whoever they have contact with, it then goes to those people, and then they all have contact with people, and it goes to those people, right? So the spread of COVID-19 modeled an exponential growth pattern when it first was introduced. It's kind of bounced up and down since then, and it's but it falls back into some exponential patterns every once in a while now. So that's what we see here, right? It fires on up. So again, I asked, relating this back to our linear functions unit, how is this different from the graphs that we saw in Unit 3? What could we say is like some of the major differences? Yeah, all right, that is correct. It is not linear, right? It is not a line. All right, what else could we say? Compared to our other graphs. If it's not linear, what kind of a shape or thing could we say that it is? Yes, Miguel, exactly. It's curved. Right? And actually in mathematics, we refer to things like this as curves, right? Because it is not a line. It has a bend to it, right? There's many different functions that are curves. This is the first one that we're seeing in this class, right? So this is an exponential curve. Right. All right, so visually, these are the major differences. It's definitely not a line, right? And it's curved, right? It curves up. Okay, so those are, when we're looking at a graph, right? Obviously, it's very easy to see that it's not a line in this case. All right, so now, see what the graphs look like. And many exponential growth functions will look similar to this. It just depends on how big the numbers are, how small the numbers are. So when it comes to the rules, right? The pattern of change for this example is multiplying by 3 each time you move up a value. So each stage we move in the process, or each time we increase the value of x, right? We multiply by 3. To represent repeated multiplication, we use exponents. In this case, since we are repeatedly multiplying by 3, we use 3 as the base, right, of the exponent. The base of an exponent is the big number. The exponent is the little number. Right, the number of times we multiply by 3 is determined by the stage of the process, or the x value. Right, so the exponent, right, is the placeholder for whatever stage I'm in, which we'll use x, or the x value. The number of people who start the process in this example determine the start value of the rule. In this case, the value is 1. Right? The whole process in the pay it forward example started with 1 person. Right? So when there's no stages, stage 0, there was 1 person. So we end up with the symbolic rule of y equals the start value of 1. And then in parentheses here, we have 3 to the power of x. All right. And so, right, we have kind of like in its pieces here, right? That's our start value. This is the base, which we've put in our rate of change. In this unit, it will always be called rate of change. We will not call this a slope. Slope is only used for linear functions. So in this case, this is just our rate of change. Right? And the x, right? The x is representing the stage, or how many times I've multiplied by 3. And we also have the now next rule of now times 3 equals next, starting at 1. And so this is, again, the rate of change. And the 1 is our start value. In a now next rule, the variable x, right, keeping track of the stage we're in, doesn't show up. It's not part of the now next rule. The now next rule only needs the rate of change and the start value. Right? There's no exponent that shows up. There's no x variable or anything like that that shows up in your now next rule. Okay. What questions do you guys have? What can I clarify? Okay. All right. Well, that was our introduction to exponential growth. That is the end of our presentation.